Okay, welcome back. And due to some technical issue, we'll move back to this room for the online streaming. So today we're gonna continue from yesterday.
Thank you. So so I have written down in the three properties that we discussed at the end of the talk yesterday. I mean the three properties for graph H. I mean the Erdős-Hajnal property, the polynomial Rödl property, and the barrel property. Just to make sure that we're all on the same page. And we also discussed that derived from definition, the barrel property implies the polynomial Rödl property, and implies, and which in turn implies the Erdős-Hajnal property. So so in the first part of the talk today, I'll try to convince you that these three properties are actually equivalent for any package. So I'm going to present an argument, just kind of recent by which option fact. So so this argument is a combination of the container method and the Allen-Pascal machine argument that we discussed today. Let me start with a very simplified version of the container lemma. So the setup is we are given two integers and k with almost k, and both of them are negative. And first one is a number from 0 to 1. Then we have a graph G. The property that so what to say, there's also a number R, which is an positive integer, and the graph G satisfying 1 minus epsilon raised to the power of L times G with the R. Okay. Then the conclusion here is either G has epsilon stuff, induce a graph on at least R vertices, or there are at most, let me say R to the K minus L times G raised to the power of L. Independent set of size K. Okay, so here, as you can see, this is a very simple version of the container lemma if you're familiar with the method. And so it basically says if you don't contain a sparse inducer graph on a large inducer graph into some amount, into some degree, then you cannot have too many independent sets. Okay. So let me go into the proof. So proof of lemma. Yeah, so the idea here is pretty simple. You do by induction, and I think formally. Let me say I'm going to do induction on L plus number of respect G. So of course it is going to be trivial when L is 0 or G is 0, right? I mean, if L is 0, then in this found becomes trivial. When R is the number of respect G. Of course, G only have this many subsets. And if G has no vertices, then yes, then this is also true. So we're done, and now we're going to the induction step. And the idea here is you first pick a vertex, just pick an arbitrary vertex into B. Now you look at the neighborhood of B and its non-neighbors. So here we are. So this is the neighborhood of V and G. Now we may assume without loss of generality that the first outcome in the lemma doesn't hold. So which means there is no induce a graph of G on at least our vertices, which is epsilon sparse. Okay. Yeah, so in particular, G itself is not epsilon sparse. And which means I can choose B such that this neighbor set has at least epsilon times B. So choose B of B at least epsilon times B. Okay. Now we look at the rest of the graph. The non-neighbors of B, the non-neighborhood of B has size now at most 1 minus epsilon times G. Right. Now let me call this subset, a big subset S. Great. And now I want to count the number of independent set of size K in G. And of course, I can classify these into two types. The first one consists of those not contained in B, and the second one consists of those containing B, right? So two types of independent sets. That's K. So the first one are those not containing B. The second one, those containing B. Right. So the point here is for the second type, you can actually reduce them to the independent sets living inside S. Living inside S and of size K minus 1, right? So these are actually being formed by the union of B. Let me just do this notation, union of those. Maybe let me say union R, where R is independent. G restricted on S. And R has size exactly K minus 1. Right? So now there are two types. Okay, so I'm going to do induction. I'm going to apply induction in two different ways to these two types. So for the first type, not containing B. So how many independent set of size K not containing B? The point here is every independent set not containing B is automatically an independent set of G minus B, right? So which means I can apply induction to L plus G minus 1. And so not containing B means K independent set G minus B. Right, and so there are at most. So what's the expression? R to the K minus L times G minus 1 raised to the power of L, right? Independent sets. K independent sets. Okay. Now for the second type, so as we discussed, not containing, containing V means you can reduce it to G restricted on S, and so containing V give us K independent sets in G restricted on S. The point here is now we know that S has size at most this. So we have our list 1 minus epsilon raised to the power of L G, and also at least 1 minus epsilon raised to the power of L minus 1 times S. Right. So now in this way we can apply induction with L and K replaced by L minus 1 and K minus 1. point here is now we are doing induction, so we may assume that L is at least one, right? So now induction. At most R raised to the power of k minus 1 minus R minus 1 times G. Let me say size S raised to the power of n. Okay, and this is at most. L minus 1, yeah, L minus 1, and this is at most to the k minus L times. Let me do a very trivial bound here, G to the L minus 1. And Z times K. Okay.
You could get the epsilon sparse set, but you could add v to it, right?
Excuse me.
There's two outcomes. You could get this epsilon sparse set on r minus 1 vertices.
Yeah, so I'm
But then you
assuming
can add-
that this doesn't happen.
Yeah, because you could add v to it and then.
Yeah.
No, I mean,
You didn't use R in this induction. So,
I did use R, I mean, so I use R as an upper bound.
okay, okay.
Yeah.
Yeah.
but potentially you could change R to R minus 1 in the basic. When you have H sparse in the subgraph of size R minus 1, then you can add V, still H sparse. So.
Oh, I see, yeah. I mean, I'm just trying to
Say,
be
yeah.
easy with numbers.
Yeah.
So trying not to go into technical details.
Uh-huh.
Yeah, but you're right. Thank you. So, so is that clear with these two cases? So now it suffices to combine the two inequalities and complete the induction step. Right, so now the total number of independent set of size K V is most relative K minus L times G minus 1 L plus R to the K minus L into the L minus 1. Right, and we're supposed to show that this summation is at most R to the K minus L times G raised to the power of L. Right, and this inequality is equivalent to G minus 1 L equal to L minus 1 removes E to the L. And now if you divide both sides by G to the L, and you get the inequality 1 minus 1 G raised to the power of L plus we say at most 1 minus 1. Yeah, but that is true, right? Because we're assuming L is 1. So any question?
Is that the bond after?
No, I don't think so. I mean, I think there are better bounds. But for the purpose of this talk, and I'm only going to present in this very simplified way. Yeah.
We plug in 1 minus epsilon to the L times the order of G instead of R, then the inequality, the right hand side of the inequality means that the number of independent set of size K is bounded by 1 minus epsilon to the sum exponent times G to the K. But
Also, you want to make this the upper bound.
yeah. So we plug in that number into the R in there.
Oh, I see.
Then it is a 1 minus epsilon to the sum exponent times G to the K. But it is obvious that the number of independent set of size K is bounded by the order of G choose K. Then why this bound is better than this trivial bound?
Also, why this bound is better than the trivial bound?
Yeah, if we plug in our then number to instead of R, then it is very similar to the trivial bound.
I'm not so sure if that's similar, right? Because you mean you would like, I mean, if you do the trivial bound, then you would like this to be something G to the K, if I'm not wrong?
Yeah,
Or-
G to K over maybe K factorial.
Yeah, but it is not better, right? I mean, the point here is K is fixed. Um, Yeah, I guess here in this lemma, I mean, epsilon is some variables, I mean, between 0 and 1. So you can make epsilon arbitrarily close to 1,
Oh, okay.
right? Have you?
Yeah.
Yeah. So I mean, here, so you mean if you figure L and K, then you make epsilon arbitrarily, then I think, I mean, this form covers all possible cases. Okay.
Can you go over the last inequality over there? I'm a bit confused.
I mean, this one.
No, below. No. S to the L minus one is less than G to the L minus one.
Oh yeah, that's the trivial inequality.
So you don't use inequality on R? No.
I use it in inequality on R to apply induction. I wanted to make sure that I mean, S satisfies, I mean, this condition with L replaced by L minus one. So that's why we need
That's checking the induction evidence.
yeah, that's why we need a fixed upper bound in R. Yes. So R plays the role of the upper bound.
I see.
So I think for Kyo's question, if you compare to the trivial bound, you also let L grow. Epsilon can be just 0.1. Now when you compare G to the K over K factorial, the fraction is G to the K log K. So if you take L to be much bigger than log K, you win, because here you have G to the K times L.
Ah, okay, I see.
Yeah. Any other question? Right. So so yes, I mean, we'll go to the proof now. Then it's actually easier to. All right. So in this format, I mean, this lemma is a little bit, I mean, has a bit too many variables, right? So we're gonna pull it down a little bit. So the corollary of the lemma is now I would like so in the setting of Rödl's theorem, like from yesterday, we have epsilon and we have delta. But so far in this lemma, and I mean, we haven't seen delta or anything yet. So I would like to put R to be delta times G. So we put in R delta times G. At the same time, I would like to put K to be 2 times delta. So now L and also L be something like 1 over epsilon times maybe 1 over delta, 1 over epsilon times log 1 over delta. So here I have epsilon and delta from 0 to 1. Let me assume that G has no epsilon sparse. Future graphs with at least delta times G versus Then G has utmost delta to the 1/2 and G raised to the power of H. But there is no raised to the power of K, sorry, raised to the power of K. Independent sets of size thing. Right, I mean, and the reason here is because of the choice of L. You note that 1 minus L, so 1 minus epsilon raised to the power of L, we use at most e to the minus L epsilon times L and at most L. Okay. Right. So this is going to be the form that we want to use to show. I think in the rest I'm going to show that Erdős-Hajnal implies Rödl, and then maybe you can modify the proof in the obvious way to show that Erdős-Hajnal also implies Rödl.
Is the S here the epsilon?
So yeah, that's epsilon. So so then we're gonna apply Seymour and then try to count the number of independent sets. Right, and
So you have G to the K, or here.
sorry, I think that
Oh, that
Yeah,
K
yeah.
is different from this K? Okay.
yeah. So yes, I think I already made the notation here. That here or
Oh, I see, so.
yeah, so already made I mean a choice K and L here.
So that K is.
Yeah. Okay, is 2 times L. And of course we are talking about in the integer, so there must be significant.
Yeah, but in the lemma it's G to the L, right?
Yeah, but then R is delta to, I mean, R is delta D, right? So R to the K minus L times E to the L. And now with exponent L
I
cancel that.
see. Oh, yeah. Okay.
So sorry me for being a little bit too big. But is that clear now? Okay, so now I'm going to talk about Erdős-Hajnal implies Rödl. And so what Erdős-Hajnal says is, as above, there's some C, another C coming from the Erdős-Hajnal property such that for n vertex H3 graphs. X or independent set size at least n to the C. Good. But so now let's look at a big host graph G. Now I'm trying to meet a big host graph G, which is H3. Now I want to say that for any epsilon, I can find a big epsilon sparse or epsilon dense induced graph in G. Yeah. So so the plan here is to apply this statement with n being some decently large power of epsilon inverse. So we want to so pick epsilon. So you pick n to be epsilon raised to the power of minus b for some b. And I mean, this b is supposed to be depending on c to be chosen later. Right. So, and also I'm assuming that the host graph G is huge. I mean the number of vertices of G is huge compared to n. And now if I pick an arbitrary subset, I mean vertex subset of G of size n, then by the Erdős-Hajnal property, I can see a clique or independent set inside this subset and of size at least n to the c, right? So this is sort of similar to what we see in what we saw in the Alan Paxson-Limouchi proof. So every n vertex subset G has also the same conclusion as alpha or omega at least n to the c, and this is epsilon raised to the power of minus bc. Okay. So now we're assuming that, I mean, you may assume that G has no epsilon sparse induced subgraph with epsilon maybe to the 100b vertices. So assume G has no sparse or epsilon dense. Epsilon raised to the power of 10b, for example, 10b vertices. Okay. And here I would like to apply the lemma with delta being epsilon to the 10b. So apply lemma or apply the corollary delta being epsilon to the 10b. And this k being is a k. Yeah, k being 2 times 1 over epsilon local 1 over delta. Right, and by the choice of and also at the same time, I may assume that epsilon is a very small variable, so much smaller than some very small constant depending on h. So this k is supposed to be much less than n to the c. Okay, if I choose b large enough so that it is much bigger than let me say b times epsilon 1 over epsilon times 1 over epsilon, then I'm gonna get this inequality. Okay, so this is some technical with numbers, some technically with numbers. Yeah, but again, every n vertex subset of G is gonna contain a clique or independent set of size at least n to the c, which means at least k. So now my goal is to try to count the number of independent set of size k in G. I mean independent sets and cliques of size k. So by applying this corollary, I can see now that the number of cliques or independent sets size k G is going to be at most, I mean, that bound over there, which is delta to the 1/2. So, yeah, so epsilon to the 5e times G raised to the power of k, and maybe 2 times. Right, because I'm trying to count, I mean, both the number of cliques and the number of independent set of size k. Okay, so Right, so now we have an upper bound on the number of cliques or independent set of size K in G. So what about a lower bound? I'm going to reuse the Alan-Pascal-Limousin trick from this observation. Okay, so now, sometimes cliques or independent set of size K is at least, it's like what we did yesterday, G choose N divided by G minus K choose N minus K. And this is at least G divided by N raised to the power of K. Okay. The reason here is because, again, if you pick any N vertex induced, I mean any N vertex subset, any vertex subset of size M in G, then you're going to see a clique or independent set of size K. Right now, try to enumerate. Okay, so now if I want to reach a contradiction, then I need to show that this is much bigger than this. Right, so this is actually equal to epsilon E and G raised to the power of K. Yeah, but of course, by the choice of N and B, so it's actually much bigger than 2 times epsilon to the 5D. So all what's left to do is to plug in suitable numbers and B and yeah, suitable number B depending on C. Okay. Any question?
This is where you use the fact that N to the C is at least twice.
Yeah,
At least K, right?
yeah, yeah. So yeah, so that's I mean the proof that Erdős-Hajnal implies polynomial, and of course you can modify this maybe in the obvious way to show that Erdős-Hajnal implies viral. The point here is with this viral property, I mean this condition, I mean just literally means that if you if D is large enough, and if you sample a random vertex subset of G of size about 1 over epsilon, then very good chance that that vertex subset is going to be H-free, right? And so now you can count the number of induced subgraphs of G of size N, which is H-free, and now you can repeat the same, the same numbers. So I'm not going to go into the proof, but hopefully you get the idea.
So why is it called viral?
Oh yeah, so originally it was polynomial Nikiforov, which is supposed to be much more sensible. But there are two issues with it. The first is it is too long. The second is I think we started this project during the last wave of COVID, and Seymour got some idea from the pandemic. He said, okay, so virus, right? I mean, so viral comes from virus, and so this condition induced perhaps containing this many induced perhaps means that the graph G is infected with so many viruses which are H, and so yeah, so that's the idea. So that's why the name viral popped up. Yeah, what I mean, so yes or no, it has become an official name. It's in almost every paper now. Anyway, right. So I think we still have time to talk a bit. So one of the reasons that I chose to only give a sketch of the proof of Rödl's theorem yesterday was because the proof used the regularity lemma. And the bound is simply not so good, right? This our type. And so we also discussed, the fact that recently there's been quite a few progress on trying to improve the dependence of delta on epsilon in Rödl's theorem and also in Nikiforov's theorem. And if you examine this argument, this container and Alan-Pasley machine argument closely, then you will see that any bound that any bound that you can have from the Erdős-Hajnal conjecture, so it doesn't have to be n to the c, but as long as the bound is much better than log n, then you can automatically mimic this argument to get a corresponding bound for Rödl and Nikiforov theorem. So let me try to be more clear now. So in what follows, I'm gonna talk about so in what follows, I'm gonna talk about bound by Erdős and Hajnal that was proved 30 or 40 years ago. Maybe nearly 50 years ago, because it already appeared in the very first paper from 1977. By Erdős and Hajnal. So 77 to 9. So there is a strange history here. The bound first appeared in this 77 paper, but for some reason, only until 89 that Erdős and Hajnal decided to give it full proof. So yeah, so then set up as in the conjecture, but now instead of n to the c, which is 2 to the c log n, here we have alpha g. With the g, you would list 2 to the c log n. Okay. So recall that the conjecture was like Erdős conjecture. So 2 to the c log n, right? Okay. So let me. Yeah. So this is already much better than log n. If you don't care, if you only want to talk about the local global property phenomenon that the Erdős-Hajnal conjecture predicts, and you don't care much about the bound, then this is already enough, because there's already some huge global consequence. Another thing here is, as I said just earlier, if you plug this bound into the Bucić argument, then in Rödl's theorem, so the argument would give you the fact that you could choose delta to be in 2 to the c, maybe minus c log of 1 over epsilon square in Rödl and Nikiforov. Okay. And simply the reason is just because this bound is much better than log n. I'm not going to do the numbers here, but you get the idea. Right. So in the rest of the talk today, I'm going to try to explain how Erdős and Hajnal got this, and also the proof of it, and also at the same time a common generalization of another result, Hobbes and Sudakov. Right. So let us try to think about how to get to this bound first. So what was the idea of Erdős and Hajnal? So Yeah, so what they did was to try to go away from the clique and independent set setting, and instead trying to look for the density version. And also, instead of cliques or independent sets, what they looked for was a parabotic subset. So let me say there is a theorem also by Erdős and Hajnal that for every h, you can find some big number b, such that for epsilon ranging from 0 to 1/2, if G is H-free, and what you can see is a pair of vertex subset. Then there is a pair of vertex subset. Let me see, maybe like this. Disjoint. And with size each of them, at least I think epsilon to p times g. And also, so here's the equality condition. A is epsilon sparse or epsilon dense to B. So here, what do I mean by epsilon sparse or epsilon dense to B? So here we have two vertex subsets, A and B. And by saying epsilon sparse, I mean every vertex in A has at most epsilon times B neighbor to B. So every vertex in A only sees an epsilon fraction of the vertices in B. This part is the most epsilon. And by saying epsilon dense, I mean every vertex in A only unsee at most an epsilon fraction of the people in B. Okay. So thank you. Okay. Right, so the point here is we are now in the dynamic version. And of course, we are not talking about what's happening inside A or B. We only care about what's happening between them.
The statement is not symmetric, so you don't say anything about the point between B.
Oh, yes, so I think, so from this condition, I think you can clean up some vertices in B. Right? So you can get a subset of B of size of this 1/2, C prime, such that now everybody B prime C, is 2 epsilon sparse or 2 epsilon dense, right? So there's some sort of symmetry here. If I some counting argument. Thank you. So, yeah, so how can we derive that frequency root log n bound from this? So if you remember, then I mentioned the concept of P4 graphs in the first talk yesterday, and in literature, a P4 graph is a co-graph, and there was an exercise asking you to prove that every n vertex co-graph is going to contain a clique or independent set of size about root n, at least root n, let me say. So now let me use the notation that mu G size of the largest co-graph as an induced subgraph. So automatically, what we have is going to be mu G let me say, mu G squared is the list max of a G, mu G, and the list mu G. Right, because every clique or independent set automatically induces a cograph in G. Right. Okay, so the first inequality is from exercise 1. Okay, so in this way, you can actually rewrite this theorem or any Erdős-Hajnal statement in the form mu G is at least G to the C times n. Make sense?
Is the power correct there? I think mu G is at least max, maybe bigger than square root.
Oh yeah, yes. Thank you. Yes, I got mixed up. Yeah. Yeah. This I mean, yeah, this is going to be correct. Okay. Right. So here, here you can rewrite the rewrite the Erdős-Hajnal theorem or any Erdős-Hajnal statement. In this form, and of course, this up to some change in C. But here we don't care much about the constant factor. Okay. Right. And so now, in order to derive this theorem from this density version, I would like to apply this result with epsilon being some large power of mu inverse. So I'm going to preset some number. Let me say b. So mu G to the minus b. Or some b. So b is supposed to be large and b. Yeah, so b is supposed to be large. Presumably, I mean, comparable to d. Okay. So what am I going to have now? So I have two sets A and B. And as with many statements in graph theory, I would like to prove the theorem by induction. Okay, I would like to prove the Erdős-Hajnal bound by induction on N, of course. Right. So now again, I apply with epsilon being this parameter. So what am I going to do? By induction, A is going to contain a big cograph as an induced subgraph, right? So I can get a big cograph as an induced subgraph in A. And let me say this is F, which is a cograph. The point here is F cannot be bigger than the largest cograph in G. So of course, F has size at most mu and G. Okay, no problem. So now I'm going to look at the set of vertices in B with the neighbor in F. And here I am assuming that A is epsilon sparsely B. Okay. So A is epsilon sparsely B means everybody in F sees at most an epsilon fraction of people in B. So which means the number of vertices in B the neighbor F is going to be at most F times epsilon times B, right? Which is at most mu times G times epsilon times B. But by the choice of epsilon over there, if I choose B to be large enough, say at least 2, as long as B is at least 2, then this is going to be much smaller than half of B. Right. So in other words, I mean F cannot see too many people in B. So actually, on only a very small fraction of B. And at least half the people in B, C, nobody. Which means F, in other words, let me say F is incomplete. At least half of the policies of B. Okay. Yeah. So now look at the rest of B, which is incomplete to F. Again, I apply induction. I'm gonna get the largest cograph in B, which is, which I can get by induction, right? The point here is now, let me say this is J. If I take a union of F and J, then this is again gonna be a cograph, right? So J is the largest cograph in B. So F union J, and because this is now the strong union and there are no edges between them, so F union J is a cograph.
You're taking the largest cograph and B minus the neighborhood.
Yeah, in B minus. Yeah. So let's say B prime. So this part is B prime. Is that okay to? Yeah. So this is the. Thank you. Is that clear now? Right. Yes, maybe it is a good time to erase this. This what are you doing? The rest. Well, all right. So now, just so let's look at this statement again. If we do induction directly in this form, then it is not going to be, very convenient. So mu G is at least due to the C with log n. If I take log on both sides, then I have log of mu G square, at least square, C square. Times log n, which is equivalent to mu G at least and C square divided by log of mu. So now in this form, it's going to be much more convenient for us to apply induction by combining F and J. So here's why. So again, by induction, I have F, right, is a cograph. And is at least the size of A raised to the power of C square divided by log F, right? Because F is the largest cograph of A. And this is at least A to the power of C square divided by log mu. So let me now denote mu for mu G. Okay, some obvious estimation. And what do I have for J? J is at least B raised to the power of C square, or B prime raised to the power of C square, divided by log J. And this is at least 1/2 of B raised to the power of C square over log mu. Right. So what do I have for the size of A and B? So as we said earlier, A and B means A and B coming from this theorem have size at least epsilon to the D times G. And if and as long as I plug epsilon, as long as I treat epsilon to be this quantity, so now I think maybe mu G to the -2 is enough. So A, B, or at least G divided by mu to the D. Maybe mu to the 3D. Okay, so A and B over 2 are at least maybe G. So all of these. So both of them in this A and 1/2 of B are all at least let me say G divided by mu to the 3D, so and O raised to the power of C squared over log mu. I mean, these two quantities are all less than one on the top. Okay. I mean, we're just doing some calculation. Okay, so now the point here is we have log mu here being in the denominator in the exponent. We have mu in the denominator. So these two expressions cancel each other out, right? So A C squared over log mu plus 1/2 of B raised to C squared divided by log mu. The list 2 times G divided by mu to the 3D C squared over log mu. And if you choose C squared to be sufficiently small compared to 1 over D or 1 over 3D, then this expression raised to this power is going to be beaten by 2, right? Mu to the 3D raised to the power of C squared divided by log mu is actually 2 to 3 C squared D. So as long as I can choose C to be sufficiently small, this will be much smaller than 2. Okay. So it's going to be much bigger than raised to the power of C squared by log mu. That's it. So here, let me say to C to be 1/2, or to C to be much smaller. Okay. Sorry, there's some calculation here, but I hope you get the idea. I mean, so this is so basically in what Erdős and Hajnal did. So, do you need a break or? Yeah. So I think I have 20 or 30 minutes left. But yeah, so I'm trying to be a bit faster now. So so in the topic of Erdős-Hajnal, there's actually a pretty well-known result, some sort of one-sided Erdős-Hajnal by Hobbs and Sudakov, which was proven by independent random choice method and became pretty famous in the area. So the theorem by Hobbs and Sudakov so the condition is you can find a clique or independent set of polynomial size. And what he did was instead of clique versus independent sets, he got independent set versus complete hypothesis. So every H to C positive such that every n vertex H3 as independent set size of this C or a complete apartheid subgraph each side size of this C. So it's a pretty well-known result, and it's been studied very often. I mean, one notable thing about this result is that even though it is one-sided, you can flip G, I mean, flip the host graph G to the complement, and then deduce that either it has contained a clique of polynomial size or an anti-complete pair of polynomial size, right? So this is a very notable result, and so I think last year with Alex we managed to find a new proof of a result that would generalize both, I mean, this Pop-Surikov theorem and this density version by Erdős and Hajnal. So let me tell you what that is. And now we go to the density setting, and I would like to say this is the density of Pop-Surikov theorem. So for the H, again, E is supposed to be large, and such that for every epsilon from 0 to 1/2, and every H can roughly either. When we say either, have two cases. And the first outcome is that's going to be an epsilon sparse. Induce a graph G with at least epsilon to the D G versus or there is, I mean, there exists A and B disjoint side that makes epsilon E times G, and such that A is epsilon dense. Right. So first of all, to see how this result implies this Erdős-Hajnal theorem, you can easily see that. I mean, the first outcome is actually a strengthening of the sparse pair outcome in the Erdős-Hajnal theorem, right? As long as you have a sparse induced graph, you can just sample the edges independently to get a sparse pair, right? That's not hard to see, and of course, I mean, the exponent D is going to be modified, I mean, up to some constant factor. So it's not very crucial. Okay, and to see how this result implies the Pop-Surikov result, I think we can take epsilon to be a very small power of n to the -1. So maybe let me right here. So first I come the sparse pair. I mean, up to maybe a 2 factor for the density parameter. But it's not important. That's sparse pair. So that will be fine. And put epsilon and -c for some small c. Right. I mean, the point here is, right, if you take epsilon to be this small power of 1/n, then the first outcome, I mean, via 2-round theorem, is going to give you a big independent set. And the second outcome, by doing the same trick as we just saw from this proof, I mean, you could get a complete pair, or in other words, a complete Pop-Surikov. And here, I mean, I'm using n and sine of g interchangeably. Okay. I'm not going to do the numbers.
Bring the first outcome again.
Yeah, so here if you, so let's say you have a sparse induced.
Yeah.
So now you pick, I mean you randomly partition the set of vertices into two. Right, so so there is going to be a choice, right, for which, I mean, the number of edges is going to be almost half, and then there's some technical criteria. Or just I mean doing a little bit simpler. If you want, if you don't mind in changing this epsilon, you just do pick 1/2 of the, I mean, half of the number of vertices, and now then you say every vertex, right, I mean C is at most 2 epsilon fraction of the rest of the graph, so that you can clean up the rest, right? You can get rid of those with too many neighbors here. And now you can get the rest of the right hand side, which is supposed to be sparse, to the left hand side. Make sense? So some technicalities. Right. Are you happy with the implications from the density of obstacle theorem to both results that we discussed so far? So, right, so I'm going to explain the idea behind the proof of this a little bit. And I mean, actually, what we proved was a bit stronger. I mean, I'm just going to be, I mean, which is going to be crucial behind the proof of the loglog improvement. So here again, this condition is H-free, right? And the reason that I wanted to introduce the viral property is because in many of these density theorems, the condition H-free is not that important. But the important thing here is we only need that G does not contain too many copies of H. And this condition, which I mean, would be useful for the induction purpose. So what we really proved was not H-free, but instead G with field copy H. So let me say epsilon to the B G raised to the power H. And again, I mean, this notation means the number of copies of H in G. Okay. Right. So let me. Right. So remember from the proof of the Allen-Baxter-Rimouchi theorem. So let me remind you again. So now we have two graphs, H1 and H2. Right now we want to substitute H2 for a vertex of H1. And in order to construct a copy of H, which is what we got from the substitution, what we did was to try to gather lots of copies of H1, right? And now we're going to say, I mean, there has to be a copy of H1 minus B, which can be extended in many ways, right? To the copy, I mean, to a full copy of H1 inside the host graph G. And now you look at the candidate set of vertices, I mean, of the images of V. And now you say there gotta be a copy of H2 inside that candidate set, and then you can get a copy of H. So what happened was, so many copies of H1. Now we fixed all but exactly one vertex in H1. So that was good. And now I'm going to try to modify that idea a little bit. So instead of fixing, I mean, all but exactly one vertex in H1, I'm going to fix all but two vertices in H1. So here, so now H1 becomes H in this setting. And another idea is I will try to add edges to H one by one, so that so I'm going to try to design the procedure that I can say if I have lots and lots of copies of H, for example, then I can try to build many copies of H with one more H, and by doing so. And by doing so, I'm going to fix the endpoints of the missing edge of H. So after I have got many copies of H, I'm going to fix all but the two endpoints of that edge, right? And now look at the set of candidates for the endpoints of the edge of the missing edge. Now I try to generate the set of candidate edges by examining the edges going between the two set of candidates. So again, so the idea, so let me say E is a missing edge of H. And of course here I am assuming that H has at least one missing edge. And if H is complete, then it is an exercise for you to show that this theorem is true and actually without the second outcome. Okay. But let me just go into this idea first. So let be a mixing edge of H. And now we try to generate these H plus E or vice versa. Try to generate copies of H based on copies of H. So what I said was it should be the other way around. Is assuming that we have many copies of H plus E. Now I want to generate many copies of H. So again, let me say, so here's H. Here I have an edge E with endpoints U and V. And here is the rest of H, this H minus U and V. Okay. So let's assume for a moment that I have many copies of H plus E in G. Okay. So just like what we did in the unpassable proof, there has to be, so this is a big graph G. There has to be a fixed copy of H minus UV, which can be extended in many ways to a full copy of H plus E. Right? And not only that, I mean, there actually should be many copies of H minus UV, which can be extended many ways to a copy of H plus E. So now I look at the candidate set for U. It's supposed to be for U. And this is a set of candidates supposedly for V. I mean, so let me assume, to avoid technicalities, let me just assume that U and V have different neighborhoods in H, so that these two sets are disjoint. Okay. So what this means from the fact that this copy can be extended in many ways to H is that there has to be a decent number of edges going between these two subsets. Right. So so this just said this for U. So here this for V. So there has to be a good number of edges between U and V. I mean, between these two sets, let me say A and B. Already. Is that okay? Right. So now the point here is if A and B, in between A and B, there are too many edges, or in other words, if the density between A and B is very high, then we can actually obtain the second outcome over there, which is dense outcome. right? Does that make sense? So what this amount to say is, if the second outcome over there cannot hold, then there has to be a pretty good number of non-edges between A and B. Okay, so now let me try to erase this and say. So the number of missing edges between A and B and G has to be decent. And what do we mean by decent? The number of non-edges. A and B. I mean, again, avoiding technicalities. It has to be at least say epsilon times A. Delta. Right. So now, to force the second, I mean, to force the second outcome, I also need to check that A and B have good size, right? The A and B have good size. Why? Because I already said that there are a decent number of edges between A and B, right? So what do we mean by decent number of edges? Edges between maybe from what we assume from the start, the property of H minus UV, right? Is already given this. Let me say epsilon versus some power. Let me say epsilon to the B times G squared, right? Because at the start, the number of copies of H plus E. This is because at the start, number of copies of H plus E in G is already at least some power. Let me say now epsilon to the A times G H, right? And G to the H, and of course, the number of copies of H minus UV G cannot be too many, and the trivial amount is most G raised to the power of H minus 2. So there is a slack in these two expressions, right? I mean the slack is about epsilon to G, or A means some power of epsilon times G squared.
Sorry, I didn't understand what is the H plus E means. So what is H plus E?
H plus E is H with the H E built in. So initially, in the pair UV, were not adjacent in H. So H is like so this was a missing edge.
Okay.
In H, and now we try to fill in the edge. Okay. Yeah, so let me try to say it again. So so there is a copy of H minus UV, which can be extended in many ways to H plus E. And by many, I mean this copy can be extended in at least this many ways to the copy of H plus E in G. And because of that, if you look at the set of candidates for U, the set of candidates for V, which I call A and B respectively, then the number of edges between A and B has to be at least this quantity. And for that reason, both of A and B have to be at least some power of epsilon times G. So let me just say poly epsilon times G, just to make sure. I'm not going to use too many letters for exponents. So now, assuming that I can choose, I can make D to be large enough, and assuming that the second outcome in the theorem doesn't hold, then it must be that there are a decent number of non-edges or missing edges between A and B and G. Okay, but that's going to give a decent number of copies of H in G, which extend this original copy of H minus UV. Is it clear?
I missed yesterday, why are there lots of copies of H plus E?
Oh, that's not, we are assuming, so we try to generate copies of H based on copies of H plus E. So we're assuming that. So yeah, so what I would like to say in this setting is we are always assuming that the number of copies of some graph H in general is going to be some power epsilon times the trivial bound.
Kind of reduction on number of non-edges.
Exactly. Yeah, so we try to fill in the edges another time. So if you try to write the proof down rigorously, then the starting point will be the complete graph.
But you can prove that directly.
You can prove that directly, and actually you can prove that the first outcome always has the home. So again, if you don't contain too many copies of the complete graph on H produces, then you're always going to see an induced graph of polynomial size, which is epsilon to some power times u, and which is epsilon sparsification. And that's an exercise. It's actually not hard. I mean, you can actually get it from the bookish Foxtrot argument. But so exercise. So prove what's now the that for every complete graph. If there exists let me say, that if the number of induced copies of K G is at most epsilon GA and G raised to the power of K. And the cost of epsilon point is up. And there exists an epsilon cost. Reduce the graph. This epsilon to the okay, that's gonna be the base case of the induction. Okay, so now going back to this into this sketch again. So we already said that there has to be a copy of H minus UV, which can be extended in many ways, in a decent number of ways, in H plus E. Right, but actually, I mean, if you examine count, then you will be able to see that not only one copy of H minus E has this property, but actually many copies of H minus UV have this property as well. So, how many?
5 minutes.
Okay, so to explain the last step. So yeah, so let me assume number of copies of H plus E is at least epsilon to the A times G raised to the power of H. Okay, so now I let T be the set of copies of H minus UV that can be extended in, let me say, at least epsilon to A plus 2 G squared ways. to a copy H plus E G. Okay. And of course, let me say R is set of all copies H minus U. Set of all copies of H minus U. G. So what do I have? I'm going to have that the number of copies of H plus E G is going to be at most first of all T times G squared, right? Because every copy of H minus UV can be extended in at most G square ways to a full copy of H plus E, right? And plus R times epsilon to A plus G with R times G squared. Right.
The first is R times G squared.
So this T times G squared, I'm trying to overcount. I'm overcounting the number of copies. This is at most T times G squared. I'm not going to do anything to the first component. The second component, now I'm going to do the trivial bound. R is, of course, most E to the H minus 2. So epsilon to the A plus 2 and G raised to the power of H. And again, as we assumed at the beginning, this was at least epsilon to the A and G raised to the power of H. So now you can see T times G squared has to be at least 1 minus epsilon squared times A raised to the power of G H. And this is of course bigger than 1/2. 1 to the A raised to mean times the exponent. So what this means is that T has to be at least so in other words, there are actually many copies of H minus UV with this property. So a full version, I think, hopefully will be in the lecture notes. This is just the idea, which should be very useful for tomorrow.
Okay. Let's think.